I'm going to discuss signature of atomic congestion identified in a Josephson junction through a phase-sensitive measurement. This work has been carried out in Professor Chavani group in collaboration on the series side with Matthieu Dartiailh, Igor Zutik, and Enrico Rossi for different parts of the experiment. And so most of the experimental work has been carried out by William Mayer and myself, and the gross by Josephson and Koshnier-Vikram-Massinger. So this work is included in the larger topic of trying to engineer p-type superconductivity. P-type superconductivity is a fairly interesting phase of matter, which is a priori much richer than the normal S-type superconducting phase. In particular, we have two topics of interest. One is the possibility to engineer topological superconductivity, also known as chiral p-wave superconductivity, with the idea to try to engineer to demonstrate Majorana fermions and their possible application to quantum information processing. Another possible application is in the field of superconducting Spintronic, where obviously it would be very nice to have spin polarized Cooper pairs that would be able to carry a spin current without any dissipation. However, in nature, we have only few or no naturally occurring p-type superconductors. The only candidates so far are uranium compounds, and strontium ruthenate oxide was case is still kind of an ongoing debate. Which is why nowadays people look more and more at heterostructures, usually combining the following three ingredients: a nanowire or a 2-deck semiconductor with a strong Spinorbit coupling, an epitaxial superconducting contact to induce an S-wave superconductivity of the system, and an in-plane magnetic field to use the Z-man splitting to lift the spin degeneracy. And so what we're going to look at mostly in this talk is a Josephson junction geometry, but I'm going to go back a bit at what has been done so far in that field. So in particular, in the case of topological superconductivity, the usual model, at least for 1D, is based on the Kitaev chain, in which you basically try to induce a particular pairing in such a way that you are basically going to change the ground state parity. So if we go back through the different term, the Rashba Spinorbit coupling is going to shift those two parabola. Superconductivity is necessary to have particular Hall symmetry, and then the Z-man is basically going to lift that degeneracy. So if you properly tune the chemical potential, you can be in a topological phase. So there have been a number of experiments and theory carried out on nanowires, whereas the main probe that has been used is the tunneling density of state. You expect your Majorana to appear at the edge of that chain. Basically, when you do, the Majorana is basically half an electron. So if you take the chain, the idea is either you have localized electron and you are happy, or you do some weird pairing and you have those isolated Majorana at the end of each chain. And that should give you a density of state at zero energy when you get in the proper phase. So that's what has been investigated mostly through tunneling experiment, for example, in the group of Professor Charlie Marcus. And as you increase the field, you're basically driving the topological transition, and you expect to see the appearance of that zero bias peak. One complicated issue is that the zero bias peak is far from being a unique signature to Majorana fermions. Many phenomena can give rise to similar physics. In particular, there have been a number of theory studies that show that, yeah, you can get very similar plots, and not all of them are topological, only some of them are topological. And it's kind of hard just looking at the density of state to know what's different between those ones. So that's why nowadays people are looking also at 2D alternatives. So in a 1D platform, you follow a bottom-up approach, and you have kind of a simple theory because you're in a 1D, or you believe you're in quasi 1D, so you can hope to do quite some work. But nowadays, more and more people are looking at 2D geometries, where you have a top-down approach, you kind of grow material and you are going to fab on it, which could be considered as more scalable, rather than having to place nanowire everywhere. So the main theory work is by Kenka that studies that kind of Josephson junction with a field orthogonal to the current. So in that figure it's X, in the rest of the talk it's going to be Y. So I'm mostly going to refer to the field with respect to the current direction. And so here you do, the Majorana basically are expected at the edge of the junction, which is basically fabricated by etching away the superconducting layer at the top, so that the exposed to the electron gas is going to act as a weak link in your Josephson junction. And so for people doing a lot of theory, this system with a magnetic field perpendicular to the current belongs to the BDI symmetry class. Okay, so I'm now going to show you what we can predict from theory, so that you have kind of some expectation as to what we're going to see in the experiment. So we can do basically mostly time-binding simulation of those systems, even though those tend to be challenging because of the sheer size of our junctions that I'm going to detail a bit later. So one thing you can see is that if you look at the spectrum, which is basically the spectrum when you allow the phase across your Josephson junction to vary and to minimize the free energy of the system. That is the one we're going to care mostly about, because we're not going to look at phase bias system. The phase is not a parameter that we're going to control, it's a parameter that we're going to let evolve and measure in the following. So you can see that starting from low magnetic field, at one point you see mostly a closing of the gap and the appearance of zero energy state. If you look at what is the density of state in the junction, you find mostly localized eighth state, which are going to be those Majorana fermions we're looking for. The green dashed line mark the limit of the gap. So basically, in all that area, you have aluminum, and you can see that you have a finite spatial extension of that mode under the superconducting leads. So that's one signature. You expect to see a gap, a superconducting gap closing in your system. The second thing you expect in a concomitant manner is to see a phase jump in the phase of your junction. That is going to self-tune to a value close to pi. It's non-universal, but it's going to something like this. A third signature, which is very important, because basically all those two signatures you could see in a p-type superconductor that is not chiral. You could have a gap closing, you could have a phase jump. But in such a superconductor, you would not expect any dependence on the magnetic field direction. One thing we are going to prove is that when we actually rotate the field, so that at 90 degrees it's actually now parallel to the current, we do not see the same kind of gap closing, which is what we're plotting here. And that kind of angle dependence is going to tell us that, yeah, it's actually a chiral superconductor, not just any random p-type order. However, there is also another phenomenon that we're going to discuss that can coexist with the Majorana physics. It's usually discussed in fairly different terms, so the language may be a bit different, which is the possibility to generate an anomalous phase shift. Usually in a Josephson junction, when you don't apply a phase bias across it and you are at zero phase, you don't see any current flowing. Or reciprocally, if you don't have any current flowing, you can say that the phase is either 0 or pi. What can happen in such systems is that actually you are going to have an anomalous phase, which means that zero phase bias, you do see a current, or you don't see any current at a finite phase bias. So the way we can understand that in our system that basically has an in-plane field and Spinorbit coupling is the following. Because we have an in-plane field, we are going to have a spin polarization. Now if we drive a current, and because of the Spinorbit coupling, we are going to separate spin species. So now we are going to have a spin gradient across that system because the orange spin are going to be majoritary. It turns out that this is obviously, through a reciprocal effect, should drive a current. But you do have a superconductor. So that's all going to loop back to the phase. And basically that kind of triple dependence between charge transport, spin transport, and the phase of the superconductor that is related to the charge transport is going to build up that anomalous phase that we're going to probe. Okay, that's kind of easy picture which has some limitation, but gives you an idea of why we can see that kind of effect. Interestingly, in all theoretical prediction on that effect, things I want to underline is that the anomalous phase is expected to be linear in the externally applied magnetic field. It should also have a density dependence and a dependence on the strength of the Spinorbit coupling. So if we are able to tune the strength of the Spinorbit coupling, we should be able to tune that anomalous phase. Okay? So this was kind of the theory introduction, large-scale introduction of our work. Now I'm going to go into the experimental work and show you how we can observe all those phenomena I just described. So first I'm going to present the kind of structure we're working on, which is an aluminium indium arsenide shallow quantum well, show you what kind of Josephson junction we can fabricate, and finally present the Squid, which is a superconducting quantum interference device that we use to perform those phase-sensitive measurements. Next I will start with the anomalous phase shift that I just presented, then move on to the observation of a phase jump and show you that actually does occur with a gap closing and has a proper angle dependence to elucidate p-type superconductivity, chiral p-type superconductivity. So let's get started with the material. We draw indium arsenide quantum well on an indium aluminum arsenide buffer with indium gallium arsenide barriers. Why do we care about that kind of structure? If you want to induce superconductivity in a 2D electron gas, you need your 2D electron gas to basically be coupled to your superconductor. That seems obvious, but it has to be so. So if we grow the aluminum at the top, it means that the wave function of the electron in our quantum well should kind of at least reach the surface. Otherwise, you won't have any coupling to the superconductor, or it's going to be far too weak for you to induce a good superconductivity. So that kind of structure, which is a kind of asymmetric quantum well, has been designed in such a way that if you look at the wave function of the system, it actually reaches the surface. You don't really want to be in that case because here your system is kind of nearly all at the surface. Your surface is never going to be perfect. You're going to sacrifice the mobility of the system. Yes, it's very well coupled to the superconductor, but it's a very bad conductor. So it's not that interesting. The case on the right does not interest you either because you see that the wave function completely collapsed before reaching the surface, in which case you don't have any coupling to the superconductor. So we are going to focus on the middle case with a top barrier of about 10 nanometers, where we have kind of a tiny bit, a residual wave function at the surface, so that we can have a good interface to the superconductor. So we have drawn many of those quantum wells, characterization through quantum Hall measurement. We get typical mobility in the range of about 20,000 centimeters square volt second, with a maximum mobility of about 40,000 in one sample. And overall, we have a mostly reasonable agreement between the observed mobility and the prediction. If you kind of put all scattering mechanism in the picture, you mostly understand why you observe the mobility you observe. The next thing, okay, so we do have a system that looks nice so far. Next thing we need is Spinorbit coupling interaction if we want to be in the proper kind of system. So we can actually probe Spinorbit interaction through weak anti-localization measurements. And what we found is that we are in indium arsenide, we expect mostly an Rashba type of Spinorbit coupling. And so what we observe is that the Rashba strength of the Spinorbit coupling is actually density dependent and can hence be tuned using a gate voltage, ranging from nearly zero at low density to about 150 milli-electron volt angstrom at higher density. So that's our second ingredient, our first ingredient. You are Spinorbit coupling. The next question is, can we get a good superconductivity in the system? And to test that, we're basically going to start fabricating Josephson junctions, because those can be used to probe the quality of the superconducting state induced in the 2D. So as I said, we have, so in all the following, indium arsenide is always going to be green, aluminum is going to be blue, and the gate is always going to be orange. So that's an easy thing for you to remember when you look at the geometry of the device. So what we do is basically we remove the aluminum layer from the indium arsenide. So basically you weaken the induced superconductivity in that part since you don't have a direct contact to the superconductor, and that's going to be the weak link in your Josephson junction. We can measure both the critical current and the excess current that you extrapolate from the high resistance, high bias resistance. And in both cases, we find numbers that are, if you look at the product of the critical current by the normal resistance compared to the superconducting gap, we find a value in excess of 2, which basically tells you that the induced superconductivity is fairly strong. Now we'll come back to that in the next slide. Same for the excess current, actually. We can also apply an out-of-plane magnetic field, in which case you see to have a kind of diffraction lag pattern you expect to observe, which is a Fraunhofer pattern. And we have a fairly regular Fraunhofer pattern that tells us that we have a mostly homogeneous current distribution in our junction. Interestingly, since we have a semiconductor, or the weak link, we can gate tune our junction. And so here you have a plot of the resistance of the junction as a function of the gate and the bias current. So basically the central dark blue region is a region where you have supercurrent. And you can see that we can tune the supercurrent from several microamperes to basically 0 by fully depleting our junction. Okay, so let's come back to those numbers a bit, because one idea that people had is that if you have an epitaxial contact, you draw epitaxially aluminum on your 2D, you're going to have a terrific superconductivity. Turns out the story is a tiny bit more complicated. For example, William carried out an experiment in which he compared 2 different samples with different mobility. One has a mobility of about 7,000, the other has a mobility of about 14,000. Those are different, but not extremely large difference. And we can make Josephson junction on both of them. And if you look at the critical current, the product of the critical current by the normal resistance in the low mobility sample, you find a value that is about half the gap. When you do the same thing on the high mobility sample, you're in excess of 2. That doesn't just scale as the mobility. And it means that definitely there is a difference in the transparency of the interface between those two samples, which is actually not so surprising. In those devices, since they are surface quantum well, basically the mobility is going to be strongly related to the quality of the surface. Because obviously if you degrade your surface, your 2-deck is going to suffer quite a lot. So you can assume that in a 7,000 mobility sample, the surface is not that great. And if the surface is not that great, it means you have defects at the surface. Those defects are going to impede the transfer of Cooper bursts from the superconductor to the semiconductor, and hence degrade the transparency of your interface. So we can, up to a point, correlate mobility and interface transparency in those junctions. Which means that, yeah, epitaxial contact is not necessarily enough to get a good superconducting state in those materials. So that was all for the junctions. So now I'm going to go to a squid, which is basically 2 junctions included in a loop that allow us to do phase-sensitive measurement. So on the left-hand side, you have a schematic of the device without the gate. On the right-hand side, you have an SEM picture colorized of the device. So once again, in green, you have the indium arsenide. In blue, you have the aluminum. So we form 2 Josephson junctions by etching the aluminum here and here. In the middle, we etched away the indium arsenide, so there is no conduction possible through the middle. And the funny shape we have on the aluminum is simply to avoid some things like vortex trapping or too strong flux focusing in the junction. Basically, since we have a superconductor here, no real transport is going to occur in those areas, so you should not concern yourself with them. And so on the actual SEM, we have the gate in orange, so we can gate independently each junction in the squid. So what should you expect when we measure a squid? Basically, a squid, when you're going to drive a current through, is going to maximize the phase of the sum of the phase of the junction to maximize the current, and you can control the phase difference between those 2 junctions by applying an out-of-plane magnetic field through the loop. So what you expect to see is kind of fast oscillation of the critical current, because the way you tune the phase difference is related to the area of the squid. And on top of that, you expect to see slower modulation related to the Fraunhofer pattern. Those simply slower, because if you compare the surface of the junction to the surface of the squid has a much larger surface, so you're going to see much faster effects. Okay? So let's move to the basic characterization of that device. So first here, once again, I present a map of the resistance of the device as a function of the bias current and the gate voltage. At 0 gate voltage, we have the maximum critical current of our device, which basically probe both junctions at a time. As we hit one junction, at some point we reach a plateau, which means that one junction has been fully depleted, and now we are just driving current through the other junction. If we look at what that means in terms of field, when we start here, when we have both junctions, we see that kind of pattern for the critical current. We see fast oscillation in the middle, and overall we see the Fraunhofer pattern of the junction, which is much slower. Since both junctions are identical, basically we just see one Fraunhofer pattern. Now if we fully deplete one of our junctions and we do the same measurement, we get this result, where basically you only see the Fraunhofer pattern of the junctions that has not been depleted. Which means we can easily, in the same device, both characterize single junction and access the full characterization of the squid simply by playing with the gate voltage. So now I would like to come to why the kind of experimental challenge we face in the experiment I'm going to present. So we want to do phase-sensitive measurement. One issue you have is that as soon as you're going to do multiple out-of-plane magnetic field sweeps, you're likely to see some hysteresis, either because your magnet is hysteretic or because you're going to trap vortices in the superconductor, which is going to be a problem. Because if you want to see a phase appearing and you need to compare different traces, you don't want those traces to have random offsets between them. Otherwise, you're just going to blur everything. The nice thing is that our device is gate tunable. And in particular, we know that the gate tunability is related to a tunability of the Rashba Spinorbit coupling strength. So if we change the gate, for example, we expect to see different anomalous phases, if there are. So what we're going to do is we're going to do a single magnetic field sweep, but at each point in out-of-plane field, we're going to measure at different gates, and different strengths of the Rashba Spinorbit coupling, and different anomalous phase. So that way we won't access the exact anomalous phase, we will access variation in that anomalous phase, which we are going to compare to a reference, which we are going to always set at -4 volt, simply because it's a low density state, so we expect to have a small right-path Spinobit coupling, and hence a weak anomalous phase. Okay? So this is the kind of measurement we have carried out. From left to right, we go from 50 millitesla in plane with a field perpendicular to the current to 350 millitesla still in plane perpendicular to the current. And vertically, we go from -4 volt to 0 volt. And so here we see squid oscillation, both at positive and negative bias current. At 50 millitesla, you can notice that basically the maximum of all those oscillations marked by the orange star all line up properly. You do not see any change, which is kind of expected if you have an effect related to the magnetic field and you go at low magnetic field, it's supposed to be weak. As we increase the field, however, you can see that the orange star kind of moves to the right hand side of my dashed line. The dashed line is the position of the maximum at -4 volt, which is basically my reference. And so you can see that, yes, I do see an anomalous phase developing in that case. Interestingly, you should notice that that anomalous phase is the same on both the positive and the negative branch of the current. That is an important point if you want to rule out some parasitic effect. So we can actually fit those data, so those are the solid orange lines, to extract the anomalous phase and look at how that anomalous phase is behaving with respect both with the gate and the in-plane. And so here what we get. So first let's look at the in-plane field at the bottom right. You can see that as we vary the gate voltage, the slope is changing, but most interestingly at all gates we have a fairly linear behavior, which is what we expect from theory. We expect to have an anomalous phase shift which is directly linear with the in-plane magnetic field. We can also look at the gate voltage dependence at different magnetic field, and notice that in all cases we have a kind of saturation of the effect at high gate, which is not necessarily surprising. We know that we can interpret it in different ways, but basically here either the Spinobit stop changing or stop changing in a commensurate way with the density to always produce the same anomalous phase. So we can also look at, do we have an angle dependence? Because one point I did not insist on earlier, but is that in a Rashba dominated system, you expect to see the anomalous phase if you apply the magnetic field perpendicular to the current. If the system was Dressel-House dominated, you'd expect to see the same kind of effect, but when you apply the field parallel to the current. So since our system is supposed to be Rashba dominated, if we rotate the field, we should see a disappearance of that effect. So we tried to do that. Turns out the data we got were a bit more complicated to acquire and a bit more noisy. So the quality of the field is not as good. Overall, when we go to high gate voltage or zero gate voltage, we see a decrease of the typical value of that anomalous phase. Another issue we had is that when you apply the field parallel to the current, the superconductivity tends to die down a bit earlier. So we could not reach as high field when we apply field along the x direction, which means that overall we should see smaller phase. So it's a bit harder to get a precise measurement. But we do see that, yes, overall the anomalous phase is decreasing when we rotate away from a field perfectly aligned along y. So far we kind of remain at fairly low field, so now the big question is, okay, if we go to higher field, can we induce a topological phase transition? And can we see something different? Can we see a phase signature of that transition? Oh, sorry, actually I forgot that. Yeah, so one thing I just want to come back for is kind of the fact that predicting the anomalous phase shift is not an easy problem from the theory point of view. Most of the existing theory assume that the induced superconductivity is weak, either because they are close to TC or because there is a large contact resistance, which both hypotheses which are obviously false in our case. We are fairly transparent contact and we are at low temperature. Furthermore, in our junction, the mean free pass is typically 100 nanometers, which is exactly the gap of our junction. Our junction gap is 100 nanometers. And the coherence length is about 300 nanometers, which means that it's not easy to decide if you're not very ballistic or very diffusive, long, short. All those things are kind of mixed up, which obviously complicate a bit the theory. Furthermore, if you want to do numerics, the size of the system is going to be a problem. The gap is 100 nanometers, that's mostly fine. The width of the junction is 4 micron. So if you start to do tight binding simulation, you need a very fine grid properly discretize that, in particular if you want to reach the kind of high density we work at, which is basically to tell you that basically we don't have a good theoretical model of the value we measure. In particular, if I go back a tiny bit, we see that you reach value of about pi/2. If you look at theory, usually you get 0.1 radian at most in an optimistic situation. So we observe an effect that is much, much larger than anything that's been predicted so far. Yeah, so let's go back to what I wanted to tell about higher magnetic field. So once again, same kind of map, low magnetic field, we are perfectly aligned. Now we go up to 850 millitesla, so much higher than before. Once again, you see that the maximum is shifting, and here you can notice that actually the shift between those two gate voltages is much larger than usual. Here you kind of shifting by some amount of pi, here you have a phase shift of about pi when you simply drive the gate voltage. So that was a kind of first indication that you can see directly in the raw data that something fairly dramatic is happening in the system when we go both to reasonably high gate voltage and high field. We can actually try to once again do the same fitting to try to see what we expect, what we get. So if we're at low gate voltage, we see something linear. Interestingly, all the linear fit presented here are only done on the points on the left-hand side of the dashed line. So for example, you can see that those blue points, all those points kind of fall in line without any adjustable parameter. They just perfectly agree with the low field data. It's a bit less true for the orange ones, but still kind of all. And you can see very clearly that the green one, red one, and purple one do see some kind of phase jump at one field. To look at it more clearly, we can actually subtract the slope we identified at low field, and we get the bottom right figure, where everything's flat for the two lower gate voltage, and we see a phase jump of about pi for the three other gate voltage. The value is not universal. We see different value for the different gate voltage. Interestingly, we can also notice that at high field, everything flattens out mostly compared to the slope we extracted at low field. So we kind of still have the same slope after the phase jump than we had before the phase jump. Okay, so this was one of the possible signatures of a transition towards a p-type superconductor. Now the big question is, can we observe the other? We discussed phase jump. We should see a gap closing and reopening, and we should see some kind of angle dependence of those properties. As for the gap closing, we do see something very similar to that. So if we go at low gate voltage, notice that this is the other junction of the squid. Everything I discussed so far was on one junction. Now I'm switching to the other junction for a couple of slides. So at low gate voltage, we see simply the gap closing in a monotonic manner as we increase the magnetic field. However, if I go to higher gate voltage, now I can see that the gap at one point closes and then reopens. Obviously, the reopening is small, but it's a real reopening, meaning that I do have a zero resistance state in the gap of that situation. The position basically match the position of the phase jump, so those two phenomena occur at the same magnetic field, and so we do expect to have some p-type superconductivity above the gap closing. We can also try to map, so now that's on the other junction, where is that gap closing happening as a function of both the gate voltage and the magnetic field. So here we plot the zero bias resistance that should allow us to identify a gap closing as a function of the in-plane field and the gate voltage. At low gate voltage, we never see a gap closing. We don't see anything happening. As we increase the gate, we can see a contour of finite resistance showing up in our data. The resistance appears to be weaker. The peak in resistance is basically weaker at high gate voltage. We don't have a good explanation for that, but that's what we observed. And we have a fairly large domain of parameters where we expect to see something like p-type superconductivity, which is after the gap closing. Finally, we can look at the angle dependence, because all that could be a trivial p-type superconductor. It doesn't have to be chiral. It doesn't necessarily host Majorana mode. If it is chiral, it should be strongly angle dependent. If we look at the angle dependence, so we start at zero magnetic field where we see a kind of very nice closing of the superconducting gap and reopening, and we go to different angles. So the angle is counted with respect to the y direction. So zero, theta equals 0 means the field is perpendicular to the current as we move away, we are going to a parallel compounding. So we see that here, okay, we have kind of a reduction of the gap, but we don't have an actual gap closing, not anymore. But we still see some kind of increasing, again, at higher field. At 10 degrees, we basically see something a bit different. We don't see any kind of minimum, but at one point the gap stopped changing with magnetic field. So it's not yet a monotonic decrease. However, at 20 degrees, we do see a monotonic decrease of the gap. No closing, nothing that could be associated with a kind of reopening. So we do have an angle dependence which allows us to rule out non-topological explanation for those observations. So the last thing we can look at is, you can say, okay, what is this? Well, what kind of phase is that? Is that a kind of mixed phase or something? So one thing we can try to look at is how the phase is behaving across that transition. Because obviously something kind of going on, but we don't really know why. So we can do the same kind of phase measurement. We have a tiny bit less points than on the main data set. So once again, we have the linearity, and once again, we see a kind of jump. If we remove the slope, what we get is, okay, we see kind of weak phase jump, less than pi. But there is still something happening when we go across that non-really gap closing. There is still something changing in the order parameter, most likely. But we cannot perfectly quantify it. It may be a mixed order, maybe something else. So in conclusion, I hope I have convinced you that in our system we can have a strong induced superconductivity through a proper engineering of the quantum web. We have a gate-tunable anomalous phase shift, which will relate to our ability to tune the strength of the right-path Spinorbit coupling. And we have observed 3 signatures which are perfectly in agreement with the observation of a topological phase transition. A gap closing and clean reopening, a coincident phase jump, which mostly agree with theory, and a dependence on both gate voltage and field, and something I should have added, which is the angle dependence that allows us to rule out trivial theta of superconductivity. Last point I would like to really insist on is that in that system, we reach the topological transition without any phase bias. Basically, our junction is never truly phase biased. We don't fix the phase of our junction, which is in contrast with some other recent experiments by other groups which actually look at a phase bias situation. Our junction is not phase biased, it's simply self-tuning its phase in the topological transition. And so one thing you could have seen in the theory is that you could see those zero energy modes kind of still oscillating, which means that we probably still have some kind of overlap between our Majorana fermions mode, which is not something we would like. One recent idea that we hope to test in the future that has been proposed in the group of Professor Aikmerov is the idea to go towards a zigzag junction. So not having a straight junction, like, okay, I'm going to have to go too far. But not having a straight junction, but having something zigzaggy, simply saying that basically now an electron starting from one Majorana fermion has nowhere to reach the other one, which would increase the localization according to the theory calculation. Finally, I would like to thank everything on the team at NYU in the group of Professor Shabani, and our theory colleagues, so Enrico Rossi from the College of Williams Mary, Alex Matthieu from Wayne State University, and Igor Zutik from SUNY Buffalo. And so all the results I've presented are detailed in those 2 archive papers, one of them focusing on the anomalous phase shift, the other one focusing on the topological phase transition and the different signatures we have observed. And with that, I would like to thank you for your attention.